Can you recognize the rule for making this sequence of curves? These are called dragon curves, or the dragon curve. There's actually a few different ways to approach making them, and they can be generated infinitely. Keep watching the video to see what they will turn into, and how it relates to Jurassic Park, the basis of calculus, and the coast of England. Let me show you how I first realized the pattern. You can look at the sequence as rotating its components by 90 degrees, attaching it to its original form, and then repeating. Turns out another way to do this is by folding a paper in half over and over again, and then following the folds with 90-degree angles. Practically, this gets a little bit tricky. However, if you could just keep folding the paper and getting them at those angles, it would create these dragon curves. And this is what it would look like over many repetitions. See here that the pattern begins to repeat itself on varying scales. The dragon curves form a fractal. They can also be tiled together. The curves were first studied by three NASA physicists, John Highway, Bruce Banks, and William Harder. It became popular in the 1960s after being published in the Scientific American under Mathematical Games. A few decades later, it was used in the Jurassic Park novel, representing the reproduction of dinosaurs. In fact, the curve is sometimes known as the Jurassic Park dragon. So there you have some of the history behind it, but let's jump into a bit of the math that's going on. If you've heard about fractals, you may have also heard about their infinite perimeters. Here is another fractal known as the Koch snowflake, where we just keep adding triangles. I think it's fairly intuitive that the perimeter of this one will be infinite because we just keep adding new boundaries to it. It may be a little less intuitive for the dragon curve, especially if we think about it as folding a piece of paper. How can the perimeter be infinite if we started with a piece of paper with definite length? Well, not to get off topic, but what is the length of the coast of England? Imagine we wanted to measure the coast, so we walked all the way around, measuring how far we've gone. If we were taking large steps, what if we missed a few little outcrops or something? Well, we just need to take baby steps all the way around the coast to make sure we don't miss anything. Although, that's still not quite good enough. Our shoes have some length to them. What if we miss an outcrop that's smaller than our shoes? Mathematically, you could use smaller and smaller units of measure to go all the way around the coast. In fact, you could go infinitely small. However, using that infinitely small unit of measure, it would take an infinite amount of time to actually measure the coastline. And thus, you would find that it is infinitely long. So we've found that the dragon curve, along with other fractals, will have an infinite perimeter. But what about the area? there's an interesting pattern with the size of these dragon curve segments. They scale as multiples of the square root of 2. So mathematicians use this to determine an equation for the area bounded by the dragon curves. I would suggest checking out their paper if you're interested, but I'll summarize some of their findings. Let's draw out the first few curves and write down some numbers. Let's use I to represent the number of steps or iterations, so we'll start with 0, and n is the number of segments. The authors use squares to approximate the area. Let's say the first one is half a square, and the side length is the length of our line, which is just a. The next step will be iteration 1. It has 2 segments, and we can approximate the area as 1 square with side length smaller than the first one by root 2. The second iteration has 4 segments, takes up roughly 2 squares of area, and once again the side lengths decrease by a factor of root 2. And for that, it's root 2 squared, so we can just write that as a over 2. Let's go ahead and do one more. So now we're on the third iteration. There are 8 segments, and the area approximately covers 4 squares. Once again, we divide the side length of those squares by the square root of 2, and this should be enough to recognize a pattern. The number of curve segments increases as 2 to the power of the iteration. The side lengths are divided by the square root of 2 on each step, and you can also write that as the square root of 2 over 2. And lastly, we have roughly 1 square of area for every 2 segments. From here we can find the equation for the curve's area on any given step. It will be the number of squares multiplied by the area of those squares, which are just the side lengths squared. If we want to find the final area, what we can do is take the limit of this equation as the iteration's variable I goes to infinity. This limit concept is also the basis of calculus. So we'll go ahead and plug in the relationships that we found earlier for the side lengths and the squares per segment. We can take anything out of the limit that doesn't have an I variable attached to it. They're unaffected. And it turns out everything in the limit will then cancel to 1. So the final area is just our starting line length squared divided by 2. So really, over all these iterations, the approximate area doesn't change. It simply takes on different and increasingly complex shapes.